see if it's actually, hey, there we go. Welcome to the first lecture in my GPU computing series. My name is Will Landau. I'm a third year in statistics here. And this short course today is going to be 2 hours, and it's meant to condense everything that I'm going to talk about later. And it's meant to sort of be a substitute for the later talks, but certainly you can come to the later talks to learn things that I say here now more in depth. So, like I said, this is a short course, GPU computing for statisticians. And this is sort of the breakdown of what I'm going to talk about. I've got, going to talk a little bit about intro to GPUs in general. I'm going to talk about CUDA specifically. CUDA is an architecture of GPUs that's been around for a few years now that makes things easier for scientists and statisticians. There are some GPU computing options in R that I'm going to talk about. One package in particular called GPU tools. I'm going to talk about next is more digging into how parallelism works, and then most of my talk is going to be on coded examples. I took my 5 best examples from the later talks, or what I think are the 5 best examples that I have, pedagogically speaking, and I'm going to run through those and sort of explain how things work and how the code that you would do on CUDA works, by example. And I'll treat this more generally and more in depth in the later talks. Let's see, does this? So there's this thing called, or a set of situations or a programming paradigm called a single instruction multiple data paradigm. Hang on, I'm just going to try to fix my pointer here. Sometimes it doesn't like to cooperate. Well, that's why the computer's up here. Gotta get this ironed out sometime. Anyway, so single instruction multiple data paradigm. It's exactly what it sounds like. You have this one set of instructions, this one piece of code that you're applying to multiple places in your data over and over and over again. And usually this happens sequentially. A good example is a for loop. This is an example of a for loop for vector addition. For I equals 0 up to 1,000,000 minus 1, you just take this vector A and set the ith element to A to be the ith element of some vector B plus that of C. You just sum all these pairs from different from vectors B and C, put them into A, and you're summing 1,000,000 pairs. What if you could do each iteration of this loop, all the iterations at the same time? This is exactly what GPU computing is going to do. So on CPUs, these iterations run sequentially unless you're coding in some CPU parallel paradigm with maybe 8 cores or something, and you give each core part of this loop. Usually they run sequentially. With GPUs, we can run all 1,000,000 of these iterations at the same time, and the code in what I'm going to introduce as CUDA C will just have similar 2 lines, except that we're going to divide up. We're going to spawn what are called threads, and each thread is sort of going to be an instance of your instruction. And you have 1,000,000 of these threads, and each thread is going to take one pair and sum it up. And that's what it's all about. We're going to split up the sort of engine of, well, informally engine you're going to split up the instance of your program into a lot of different threads, and those threads are going to run all at the same time. And you get much, much faster computation on the GPU for reasons that I'm going to explain later. So this is the sort of place where you would want to have GPU computing. There are a lot of really long loops, a lot of things that get repeated over and over again. I'm sure you can think of in your own research examples where you might want to parallelize like this. And so You see a situation like this, think maybe you want to use GPU computing. So here's an example in practice of somebody who did an MCMC and got a lot of speed up. So what these guys did, Lee, Yao, and Giles, they implemented a lot of different parallel algorithms. One was an MCMC that they describe in their paper. It's in the references in these set of slides. And they parallelized their MCMC across chains. They increased the number of chains. And initially, the CPU time is about the same as the GPU time. This GTX 280, that's a model of GPU. And you don't get very much speed up. Speed up I'm defining as CPU time over GPU time. Once you increase the number of chains, you get this almost 300-fold speed up in their code for about 100,000 chains. So this is not, this is not, two-fold, three-fold speed up. This is potentially 100-fold or even 1,000-fold speed up, which makes an amazing amount of difference.
Running the chains parallel.
Yes. Yep. But you don't have to parallelize across chains. You can parallelize across, parts of your data. You can, so you would get, this speed up as you increase the sample size of something like sequential Monte Carlo, which is in the same paper. They parallelize across their data. And as you increase the sample size, again, you get a ton of speed up. You can get a speed up of up to 31,000 in this case, which is pretty amazing. That's from the same paper. There's also another paper by Suchard, Wang, and Chen that I have in the references where they describe their algorithms and how they parallelize them. This is a Bayesian E&M algorithm. And again, they parallelized across the data. As you increase sample size, you get more than 100-fold speed up, or at least they did. And they define what their CPU1 and GPU1 were. I'm not going to go through their hardware here. They tested, on a couple different sets of hardware too, and they got similar speed ups. So this is done successfully in practice, and it's documented. So there are a bunch of other applications too. There is clustering. I'm going to go over a k-means clustering example today and a few talks later, where you can, because clustering involves comparing a bunch of different points to their current sample mean and updating how you partition those points and updating the means of the clusters. And there's a lot of opportunity for parallelism there if you're doing, say, something like simple Lloyd's k-means. Other examples of clustering are a bit harder. If you do k-means with Hartigan-Wong's algorithm, parallelism is a bit harder, but it's still doable. There's Bootstrap. The thing about Bootstrap and about MCMC is uses a lot of random number generation. You're going to want to generate random numbers fast, a lot of them. And there's this library in NVIDIA's toolkit. So NVIDIA is a company that makes a lot of GPUs. It's one of the predominant GPU retailers in terms of hardware, and it has a lot of software libraries for GPUs. And one of them is called cuRAND, and that's for generating random numbers. And you can do random number generation pretty easily in parallel with that library. You don't really have to implement your own random number generator unless you want to use some state-of-the-art algorithm that hasn't caught up, that NVIDIA hasn't implemented yet. There's regression. I'll show an example of ordinary least squares today. There's a library with a built-in simple linear regression available. There are also libraries based on BLAS and LAPACK that do really good matrix multiplication and matrix inversion in parallel. It's pretty simple to use, and I'll show those today too. Like I said, matrix algebra goes along with regression. EM algorithm, we already saw the speed up in a Bayesian EM algorithm, but frequentist EM algorithm can be parallelized too. There's rejection sampling. obviously, it goes along with the speed at which you sample a lot of random numbers in parallel. Multiple testing scenario. If you can think about multiple testing, the thing about multiple testing is obviously you have multiple tests to do. If you do all of those tests at once, maybe you're going to get a faster result than if you do all of those 10,000 or 5,000 tests that you would need to do if you're analyzing something like RNA-seq data, where you want a test for a difference in gene expression across treatment groups for every single gene. And you usually have about 3,000 or 5,000 genes. And you could write a package that does all those tests at once, and things would go much faster. There's also cross-validation. Dr. De Brabanter here was telling me earlier that he's working on a support vector machine package for MATLAB, right? Where there's a part where he needs to do cross-validation. Now, the thing about cross-validation is that you take your whole data set and you take a training set and you partition it into a training set and a testing set, right? But there are multiple ways you could do that partition. And so what a lot of people do if they want to do it rigorously is take multiple partitions of the data into training and testing. And they loop through all of those sequentially. What if you could assign each parallel thread to take care of just one partition? That's sort of an embarrassingly parallel situation where you could get a lot of speed up there as well. And there are plenty more examples. I mean, there's plenty of examples since everybody likes there are as many examples as there are really long for loops for opportunities for parallelism. All right, so that's sort of why we care. Now I'm going to get into a little bit of the hardware behind GPUs. And it's important to understand a little bit about this to understand not only how to code this, but the limitations of your code. How far you can push this GPU parallelism paradigm. So a processing unit is a computer chip that performs executive functions. A core is one of possibly many subprocessors placed in the same processing chip. It used to be that a processing unit and a core were the same thing, but with the advent of CPU parallelism, each processor was actually divided into multiple processors that were all nested together on the motherboard. So you could parallelize things across different cores, and you'll hear things like a dual core processor, for example, or maybe even an 8-core processor, and people have those now. I don't know if they make 16-core processors yet for CPUs, but not yet. No? I know they've gone up to 8. I don't know if they've gone up to 16. An 8-core processor? I've heard of them. I've heard of them for CPUs. 6 was, you thought 6 was the limit? Maybe you're right. I don't know.
Unless it happened in the last couple of months.
Oh, okay. Yeah.
We're not talking about 2 quad cores, right?
Okay. So, yeah, apparently there's an 8-core CPU CPU out there. Thing about GPUs is they have about 400 of these cores. They have over 400. Our GPUs at Iowa State have 400 cores, and that's a lot more parallelism than just 8 cores. It's almost an order of magnitude more. And with the new GPUs that are coming out, maybe they have even more cores. Maybe they have. I haven't checked, but.
However, the cores have access to all the memory.
Yes, they do. Yes, they do. So the CPU is what you think of as a regular computer processor. So it allows parallelism, but not massive parallelism, because it doesn't have very many cores. Usually it contains 1 to 8 cores. There is the Intel, 8086, which is based off of the, which has what's called the x86 architecture. Many of you have heard of x86. Dates back to 1979, very far back. I know you've heard of Intel Core 2 Duo. That's ubiquitous. Here are some pictures. This is just a processing chip. Intel makes a lot of them. I know you've heard of them. Now, graphics processing unit is a little different. It's a processor in a video card. So I know you've heard of graphics cards, those of you who like gaming, video or into hardware. You know, video cards are standard for your displays. And inside a video card or graphics card is its own processing unit. Graphics cards have their own processor called a graphics processing unit. And this does massively parallel calculations. Originally designed to speed up graphics on Windows, and it really quickly took off in video games. So most of the original development of GPUs was to accelerate video games. They can't run by themselves, so you can't have a standalone GPU. It needs to be hooked up to a computer that has a CPU. It contains several hundred cores, like I said. Ours have just over 400, I think 441 or something like that. And GPUs have higher memory bandwidth than CPUs. So the on-chip memory goes back and forth to the cores much faster than in the CPU case. Some examples are the GeForce. See, there's the GTX, which was featured in the Suchard paper. I think it was a Lee paper actually. They used GTX as one of their video cards. There's several Tesla models, and that's Tesla was state of the art very recently. But I think there are some newer ones out there. They keep coming up with new ones. We have Teslas at the stat department, and here's a picture of your video card on the right, and the processor on the video card over here. This may look familiar to many of you. So here's a diagram of sort of what happens in each, or what's in each processor. We've got the CPU over here, and let's say there's a graphics card hooked up to it, and this is the GPU. So we've got our memory, and we've got our cores. This happens to be a very advanced CPU with 8 cores, with a lot of bandwidth between them, obviously. We could have just kind of stuck them together, too, in a schematic. The width of these lines represents how fast you can communicate between, let's say, memory and cores. The width of this line is proportional to the speed at which you can write things back and forth, which is what I mean by bandwidth, or how much traffic there can be here. So,
Is it the same as the bus?
I don't know. I think in most cases it is, but I'm not exactly sure. I mean, some things like inside here, I mean, is just one chip. So this is on-chip memory. So I'm not sure if you even, I don't know if they have buses on chip, or if buses are just between chips. I'm not exactly sure about that, but a lot of these could be buses. But they're not necessarily buses, all of them. Certainly this is a bus. But what this diagram shows is, I mean, thickness is proportional to bandwidth. Yes. So there can be a lot of traffic between cores on the CPU side. Notice this line is thicker than this one. The massive number of cores can write tune from on-chip memory much faster than the CPU counterparts, which is great for GPUs. Not only do you have a lot of cores, but this memory over here, most of which is shared memory and register memory, you can write things really fast here.
One question, the memory here, is that the system memory or is that the chip memory?
This is chip memory. Yeah, this is not system memory. Yeah, so this will include registers and I think on-chip caches if you have them. But these thinner lines, so that the on-chip memory communication between the CPU cores and on-chip memory is slower in a CPU, and the communication between CPU and GPU is very slow. So that's one of the reasons why if you start a program on the GPU, it may take a while to initialize, and it may take a while to write everything to the GPU. So that's one of the limitations of GPU computing for big data. If you want to write all your data to the GPU, it's going to take a lot of time. So I mean, the potential speed up may outweigh that disadvantage, but just be aware that the CPU-GPU communication takes a lot of time, and you want to avoid that whenever possible. So you want to avoid writes to the GPU and back to the CPU whenever you can. You can't always, clearly, but just, I would say, don't write excessively to the GPU. Once you're there, though, you got hundreds of cores, and you've got really high memory bandwidth. All right. And how it works is, what I forgot to say was, the CPU is sort of the thinking part, and the GPU is sort of the pocket calculator part. You know, if you're doing sort of a computation, you know, on paper, and you get to a point where you need to do a long division of a really, really big number, like a 6-digit number, by, you know, by 12 or 13 or something, you're not going to do it in your head. You're going to just plug it into the calculator and then read the result that you get, right? The CPU is sort of an intelligent program that will always be based on the CPU. Will say, I have this really dumb calculation coming up that I want to apply to a lot of different places in my data over and over again. That's too menial for me. I don't want to do that. I'm going to make the GPU do that. I'm going to make multiple workhorses, multiple cores in the GPU, get that done really fast, and then I'm going to read that result back. So that's how you want to think when you're writing an algorithm for the GPU. The GPU doesn't do everything. For example, it's really hard to make the GPU print to the screen. There's a source file and a header file out there. I think it's called cuprintf, but I mean I haven't tried it. But it's sort of really hard to force the GPU to print something, for example. The GPU doesn't have access to the rest of the hardware. It's not going to have access to I mean, it's not going to have access to your hard drive. It's not going to have access to, you know, your USB storage devices, and it's not going to have access to a network also. So you're going to have to micromanage everything through the CPU. Moving on. There's this other bit of how to wield the GPU effectively. Once things are on the GPU, you can parallelize them, which is, as I said before, running multiple calculations simultaneously through what are called threads. So, in the architecture that I just described for the GPU is specifically suited for massive parallelism. You have a lot of those cores, higher memory bandwidth on chip. The architecture is suited to parallelism. There are other kinds of parallelism, though. I'm going to talk about GPU parallelism. I'm going to talk about parallelism for short. There are other kinds of parallelism. There's POSIX threads. Does pthread create ring a bell for anyone? Yeah? That's POSIX threads. Using functions like pthread create and locks and mutexes to manage, you know, threads on the CPU, which is important for CPU computing. It's why you can, you know, open Firefox in one window and open Word in another window, and within Word you may be able to click save and work on your Word document at the same time. There's multi-threading on the CPU, and it's very important for you know, the way operating systems work. That's not going to do much else for science. There's parallel cloud computing. I don't know anything about that, but it exists. There's OpenMP, which has been around for a while. And there's also OpenCL. OpenCL is relatively new. It's attempting to be some sort of universal language for just any architecture and support parallelism. So you don't really need to, if you do programming in OpenCL, the idea is maybe you don't have to micromanage the hardware, but you can still write parallel code. That's relatively new. And what can you gain from parallelism? Well, theoretically, you would go to Amdahl's law, which says that the maximum speed up in terms of time is this expression, where in this expression, P is the fraction of the program that can be parallelized. In terms of execution time, the fraction of time in a program that can be done in parallel. and n is the number of cores, or parallel processors. And as you increase the number of parallel processors, you get a speed up of 1 over 1 minus p, which becomes really good if you can parallelize something like 99% of your program. If you can parallelize 99% of it, you can get a 100-fold speed up, theoretically. That's maximum. The other thing, though, is this is just for parallelism across cores. I guess that's a limitation on Amdahl's law. It doesn't account for the fact that cores can multitask. So the core can, on a CPU, you can think of a core, doing some arithmetic, and then the user tells it, tells the computer read something from the disk. So it sends a signal to the disk, and then it waits for a response because, disk CPU communication is really slow. While it's waiting for a response from the disk, it's going to go back and do its arithmetic. It's like, if you're cooking dinner and you're making soup and you're baking bread, right? You mix the bread dough and then you let it rise, and then you don't wait for it to rise before you start making the soup. You wait for the bread to rise, and while you're doing that, you chop vegetables. So that means that the sum time that it takes you to bake bread and cook soup is going to be less than the time that you would spend cooking each individually. And so maybe in theory, with a lot of cores, you might even be able to do better than this if processors multitask really well. But in practice, though, you're not going to get better than Amdahl's law says. All right, so that's GPUs and a little bit about parallelism, why it's important. Let's go to CUDA, which is a specific architecture, and our CUDA systems. Let me see if we're good on time. All right. So GPUs were originally meant to speed up graphical displays for Windows and video games. If anyone remembers Duke Nukem 3D, that's one of the first places where people went and got graphics cards for. This should bring back memories for some of you. So CUDA, on the other hand, now games like this were programmed in some graphical languages that were based on the worldview that everything is in a 3D bitmap. All right, and in science that's not always the case. You don't always want to formulate your problem as a 3D bitmap. You may want to code in something like C, which is very good for fast numerical calculations. Well, some people went to the GPU and made a whole different architecture for GPU that's specifically designed to be programmable in a language similar to C. And so we have CUDA, which is Compute Unified Device Architecture. It's built to support a C-style language and to be able to be used for multi-purpose calculations and not just displays. So this is the first time that GPUs were used for something other than graphics. So, like I said, before CUDA, you could only use a gaming graphics language for scientific computing, and people did that for a little while. And then CUDA was invented, and now there's this thing called CUDA C, or CUDA C++, which is really easy to pick up if you know C or C++. Knowing C++ makes it even better. So we have CUDA-enabled servers. There's Impact 1 through 4. Impact 1 currently works. Impact 2 is down right now as far as the GPUs are concerned, and I think the rest are down. They were working. I talked to the IT guys recently, and so yesterday what's that?
I said last year also the slide is the same.
Yeah. Well, we didn't actually have Impact 2 through 4 yet. You can log on to Impact 2 through 4. The CPU side is working. Before, this time last year, we didn't even have Impact 2 through 4. Now we have them. Impact 2 worked for a while, and now it's down as far as the GPUs are concerned. I was using it this summer. What's that? They're still trying to figure it out. Yeah, Jared said they were using it to play video games. No, they're running into hardware issues, and they just tried to fix them today, and they fixed Impact 1, which is down when I tested it last night. But it's We have Impact 1 that works for GPUs right now. The rest you can log on to. So they're Red Hat systems, presumably because Red Hat has tech support. There could have been other options, though. What's that?
I thought it was now CentOS. It's not CentOS?
I heard it was Red Hat, at least for a while. Maybe it was changed to CentOS. Okay. Yeah. I haven't updated this slide actually since last year, so they could have made the switch. I'm not sure. Okay. So maybe CentOS. It may not be Red Hat, but yeah, this time last year it was Red Hat, and I haven't really checked since. Mm-hmm. Mm-hmm. Yeah. We don't have a graphical user interface, so you're going to need to use the Linux command line. If you don't know how to use the Linux command line, you can talk to me. I could demonstrate a little bit today if you want to. Each has 24 CPUs and 4 Tesla N2070 GPUs. Each of those has 448 cores, each GPU. And for more specs, you can log on to Impact 1, 2, or 3 and enter this thing. So you can go to the NVIDIA Software Development Kit and then run device query. So I'm going to demonstrate that right now, I guess, especially for those of you online. So let me take a look at my bash RC file just to show you that I have, as an alias right here, I can just hit I in my terminal. This program is terminal, by the way, on Macs. I can just hit I, and I log into Impact 1. And this is the command to log into Impact 1. I'm just going to copy it and show you. So I just shell in. It's going to take a while to log. Well, I'm already logged on. And I can change CD into user, the local folder, oops, forgot the backslash at the beginning. I'm using tab completion here. Every time I hit tab, it automatically fills the rest. C bin Linux release. All right, and I'm here. And once I'm here, I can hit device query. A / says execute in this folder, device query. And it will show me all of the GPUs, eventually, and their specs. Still running. There we go. So it detects all these cores. It'll go from device 0 to device whatever. So it says found 4 CUDA-capable devices. First one's 0, device 0. It goes up to 3, so there are 4 of them. It gives you the CUDA driver version and runtime version. I thought we had CUDA 5. Apparently, Impact 2 has CUDA 5. Impact 1, I thought they had updated to CUDA 5. Apparently, they're still on 4. You have 448 cores. It gives you the clock speed, bus width, clock rate, all bunch of other specs. And important, it gives you oh yeah, so it gives you, this will be important later, maximum dimension of a block. I'll tell you what a block is a bit later. Maximum dimension of a block and maximum dimension of a grid. So you divide your parallel tasks into things called blocks, and you divide your blocks into parallel tasks called threads. And you can have this many blocks and this many threads. And the total amount of threads, total amount of parallel things you can do is the product of all these numbers that I've highlighted, which is a lot of threads. So there's a potential for a lot of parallelism. And you're going to have multiple threads per core, but those cores can multitask. So like I said, you open a command line program. I use terminal. If you're on Windows, you're going to need to download Cygwin or MinGW, and you SSH in. I just demonstrated that. Note the port number -P323 that says the port is 323. That's not always going to be your port number necessarily. The IT guys have hooked up the impact servers so they run on that port. There's a bunch of help for Linux, Linux command line. And for any of these reasons, if you can't log on or something, you can talk to me or talk to Stat IT and we'll help you. And there are more tutorials. I'm not going to go over them, but here's a bunch of links. You can also Google Linux command line to learn. All right, so on our servers, here's some important directories. So there's your home directory, which is your private folder, and that's not actually on the impact server locally. That's on SMB, which is our collective, our collective Linux storage system for the department. So this is actually part of a drive that's mounted onto the impact servers and not actually part of them locally. Sci files, same deal, except that this is mounted from the university system on the impact servers. Temp is stored locally, but the files in here get deleted periodically. So if you want fast access to data temporarily, you might want to put them here, but keep in mind they're going to be deleted every so often, every maybe 2 weeks or so. I spent a lot of time in the introduction, so I'm going kind of fast. This is the software development kit that I just showed you. It has some example code that NVIDIA distributes with every installation of CUDA, and you can go and access it. All right, GPU computing with R. I guess I'm not doing too terribly. There are a few packages with R, not a whole lot. There's WideLM, which is for linear models. There's Magma, which does LU factorization and backsolving, which you can also do with some CUDA libraries that I'm going to tell you about later. There's CUDA BaseReg, which is specifically for fMRI data, but that model can probably generalize to other regressions. There's GCBD, which is for Debian. Unfortunately, some R packages are platform dependent. It's for more matrix algebra. Again, you can do all of this in CUDA C. You don't need to do one of these R packages for it. And then there's GPU tools, which is a machine learning package, which is probably more useful than these. So GPU tools has some machine learning, some matrix algebra. And here, you can, before you begin, you can presumably check if there are multiple graphics cards installed on a Linux server. You can first of all call get GPU ID to see which one you're running on, and then choose the graphics card you want to run from. There are a whole bunch of matrix algebra functions. There's multiplication, cross products, QR decomposition, solving for linear systems of equations, singular value decomposition, and computing distances between Euclidean points in Euclidean space, usually for the purpose of, in this case, for the purpose of clustering. That was the intention of the authors. And then there's some model filling. There's LM and GLM functions that are GPU implemented. So if you like the GLM and NL and LM functions in R and want to parallelize them, this is a quick go-to. And then there's hypothesis testing. There's t-tests. There's AUC estimates. AUC stands for area under the curve, and it's usually area under an ROC curve, receiver operating characteristic curve. And then you have a bunch of machine learning functions, like Granger causality tests and independent component analysis. And you can read up on those if you like. So I have some example code. So I just loaded GPU tools and got the idea. The graphics card that I was using, that was 0. I set the graphics card to be the third one. And for your reference, I just ran a bunch of, a couple of matrix multiplications. So I have A and B to be very large matrices. And I timed the GPU matmult function of A and B. It took about 3 seconds. on the user side, the same matrix multiplication in R took about 100 times longer, or 50 times longer. So you can already get a speed up with GPU tools for matrix multiplication. So this is something you can do right now on Impact 1. You can speed up your matrix multiplications right now if you know R. Yes? Yeah. I'm not sure if it does anything different for sparse matrices than it does for regular matrices. Probably not. So a while ago I tested GLM versus GPU GLM. I calculated the mean run times for a bunch of runs. It's hard to see that green, but it goes, I'll show you with the cursor so you can all see even online. Green line goes about to here. So x-axis is base 2 of the number of observations in your model. If we go past 10 to the 5 observations, you start to see a speed up. It takes a while though. I mean, if you're working with small data or small workflows, you're more than likely just better using doing that on the CPU. But once you get to really large amounts of computation, you'll want to go to the GPU. So, and here's a this is not done by me, this graph. This was done by the authors of GPU tools to test their implementation of Granger causality tests. That's testing if, one time series, and it's testing something about the relationship between two different time series. And as you can see, the GPU time, stays constant, very with relative to the CPU time with the number of random variables. At least it doesn't increase very much with the number of random variables. But the CPU, the equivalent CPU implementation is you increase number of random variables, you quickly get a lot slower. All right. So now 50 minutes into lecture. This is more time than I wanted to spend on introduction. But the regular talks are going to go like this. So intro and GPU tools. This is what I just did, actually. If you don't, so you don't need to come next time because I already covered that information here. The next talk, which I'm not going to do much of today, is a codeless intro to GPU parallelism. That's with just no code. I explain how to parallelize some simple algorithms so you can start thinking about, how you want to write your code. Then I go into a bunch of lectures on CUDA C. So I introduce it in the third lecture. That's 3 weeks from now. And then I go right into some examples. So 4 weeks from now, and today, if I get to it, I'm going to go over a k-means and an MCMC. There's micromanagement of memory and performance, and measuring performance on the GPU. That's a bit more advanced. But if you're doing some serious coding, you'll want to get into those things. And then race conditions, atomics. Those are topics that are more important to POSIX threads than to GPU parallelism. But since I learned POSIX threads first, or attempted to learn POSIX threads, I really never got the hang of it. My bias is to include those topics here. And I'm going to talk about warps too, which are just another grouping of threads. A couple libraries the next time, Kublas and Kula. Those are for linear algebra. Kublas is the equivalent of BLAS, basic linear algebra subroutines. It was implemented originally in Fortran, still is. Used a lot in C. There's a GPU accelerated version of this that's very good, that a lot of people use. Yeah, presumably. I'm not actually sure, but how else would you parallelize? I guess because there's no, as far as I know, a GPU equivalent of Fortran. So I think they're written in CUDA C. There's certainly, you can call those functions without having to do anything special with Fortran. Although there is a section of Fortran and relating Fortran to CUDA C in their documentation. Kula stands for CUDA LAPACK. It's what it sounds like. It's the CUDA implementation of LAPACK. Both are very nice. curand, CUDA library for generating random numbers. I'll spend a whole day on that. There's thrust, which is great, which is, any of you heard of STL, Standard Template Library, C++? Yeah? There is a CUDA-C version of that, which is very good. I use it a lot in, well, try to use, well, some specific features a lot in my own coding. I do a whole day in Intro to Python. Well, why am I doing that? Because the very next lecture, I talk about a PyCUDA module, which is the Python module for GPU computing, where you can actually write GPU accelerated code from within Python, and you don't actually have to, write CUDA-C code and then compile it yourself. All right. So a bit on how GPU parallelism works. We only have an hour, but I'll try to get through as much as I can. So the CPU sends, in parallelism, GPU parallelism, the CPU sends the GPU a command called a kernel. I'm going to refer to this command as a kernel. This is not, the kernel of an operating system. This is a kernel, an instruction set. Now, what the GPU does is it executes this kernel multiple times in several duplicate executions of the kernel. And these duplicate executions of the kernel that occur simultaneously are called threads, like I said before. These threads are, for purposes of convenience and hardware, are grouped into bunches called blocks. So each kernel spawns multiple blocks, and inside each block are multiple threads. And the sum total of all threads in a kernel is called a grid. You can think of a grid as sort of, from a graphics point of view, a representation of a bitmap. So bitmap is sort of like a grid. That's how it's arranged. And you can take the grid and divide it into blocks. In each block, there are multiple threads. So here's something that might happen. So the CPU might say something like to the GPU, like some pairs of adjacent numbers. That's my kernel. And I might do it to the array of numbers 1 through 8. And I might say, use 2 blocks of 2 threads each to do that. What the GPU might do is, well, like I said, that's the kernel, that's the data. And the GPU is going to spawn 2 blocks with 2 threads each. And here's what it's going to do. It's going to take block 0 and block 1, assign these 2 threads to block 0, the second and third thread to block 1, and each thread is going to take 2 numbers and sum them. First thread gets 1 and 2, second thread gets 3 and 4, and so on. And all threads happen simultaneously, so all these actions happen simultaneously. That's sort of a little toy example. I could have also used 1 block with 4 threads and given each thread a different pair of numbers. That's the sort of thing you're going to do under the hood. You're going to think about, how many blocks do I need, how many threads do I need, and what do I want each thread to do, and what do I want the blocks to do collectively. So here's a picture. So each kernel, the kernels happen sequentially. For each kernel, I get a grid. For each grid, I get multiple blocks. Each block, I get threads. Now you notice this is written in 2 dimensions. Blocks and threads actually are represented in more than just 1 dimension. They're actually, each grid has 3 dimensions of blocks. And each dimension is about 60,000 in length. And each block has 3 dimensions of threads as well. That's how it's represented. I'm only going to use 1 dimension for blocks and 1 dimension for threads in the example code that I go over. But there are more dimensions. Now I go into examples. I have exactly an hour left, and I'm going to try to get through as much as I can. I'm going to turn the fire hose on you, but that's what this short course is for. We go through a lot. I'll go over everything in more depth later. Are any questions now? Yeah?
For examples, are you going to go into Valgrind and all that stuff? Or?
I'm going to go through Valgrind when I talk about some of the examples. So it's pretty simple using Valgrind and CUDA memcheck. If I get there, some examples have them. Anything else? This is where I accelerate. And you want things explained slowly, then come to my later talks.
Yeah, just don't do all the examples in parallel.
No, I won't do all the examples in parallel because yeah, I mean making five clones right now, I can't do that. Anyway. So, vector addition. First example. I have two vectors and I want to sum them up component-wise. Like this. So each C sub I is A sub I plus B sub I. Pretty simple, right? So here's how I might do that. So what I could do is, I don't know if you can see, I have a grid, spawn a kernel, and out of that kernel I have one grid. There's one grid per kernel. And I say, well, I want one block this time, and I want each block to have, this block to have 6 threads. And each thread is going to take a pair of numbers, add them up, put them in the new vector. And I do that 6 times, once for each thread. All these threads, remember, happen in parallel. This text may be hard to read, but green is for grid, blue is for block, and red is for thread. Kind of works out. So just kind of remember what rhymes with what, and you'll figure out what this coloring scheme means. I could have also parallelized it differently. This isn't as good of an idea, but I could also do, well, actually, maybe it is. You'll have to, for each specific problem, you'll have to go online and sort of say, or you'll have to think about, how many blocks and how many threads I want. I don't always want, one block with as many threads as possible, or or a lot of blocks with just one thread each. There are a lot of options. You want to figure out which one runs the fastest. So the point is, though, here I can have a grid. I can spawn 6 blocks with one thread each. Notice I index each. This is thread 0 within block 1, for example. Thread 0 within block 2. Each thread has an index inside its block, relative to its block. So there are multiple thread zeros because there are multiple blocks. And you get, when you spawn a kernel for free, a thread index and a block index. And the thread index is always, the thread that's, first thread or second thread inside this block. And the block index is valid within the whole grid. The point is, I could also make multiple blocks, have one thread each, and do this same task. Now in practice, you're going to have multiple blocks and multiple threads in each block. And so I might do something like this. 2 blocks, 3 threads each, all doing the same thing as before. And threads go from 0 to 2 within each block. You all good?
So threads are run parallelly, or all of blocks, all of them runs parallelly?
Everything runs parallel. The option.
So why then it matters whether you putting more threads to a block or one thread in each block? If all of them are running parallelly, why it matters then?
I'm really glad you asked that. So the question was how are blocks different from threads, and what does a division of threads and blocks matter? Is that pretty much your question? So it matters at the hardware level. So blocks you can have multiple blocks per core, but blocks are never split across cores. So if you want all these threads to run on the same core, you might put them in a block. Also, and when you run your programs, not everything is going to be embarrassingly parallel. Some threads are going to need to communicate with each other to share some memory. In fact, you'll have something called shared memory that all these threads can access, but none of these threads can access. It's in a different block. You put threads in the same block that you want to communicate with each other, but communicating across threads within different blocks, communicating across blocks is very hard and very expensive, and you don't want to do that. So that's the main practical reason.
How about memory?
Memory? What?
Other than communicating, they have, how do you say, you split the memory or something, like creating a matrix partitioning or something?
I'm not sure I know what you mean.
Some partition is used by block 0,
Yes.
and another partition used by block 1.
Yes. You could, Yeah, you could.
You have natural block, right?
You do. And one implementation of matrix multiplication uses just that. I assign each block to, you know, a column of one matrix and a row of one matrix, the other matrix that are getting multiplied. And I could give some memory to this block and some memory to this block. And so you can partition shared memory across blocks and work that way very efficiently. So it does divide up the memory. Did I answer your question? Yeah? All right. So I'm going to jump right into code. This is my first coded example. Tell me if you can't see this. I can sort of zoom in if for anybody who wants to. But here's some example of code, CUDA C code. And usually I have smaller examples first, but this is the short course, so I'm going faster. First thing are the libraries. You have your regular standard IO, standard lib. CUDA.h has the headers for the CUDA drivers. That's the hardware. You don't actually always need it. I just include it just to be safe. You don't really need to unless you encounter a problem. CUDA runtime is the runtime headers. I don't want to go over how that works right now, but if something's not working, what it complains that it can't find this or that function that's supposed to be built in, you can include CUDA.h or CUDA runtime.h. N is going to be the size of my vector. I have vectors of size 10 in this example, really small. And add just takes A and B, adds them component-wise, stores them in vector C. And this __ global means this is a kernel. This function is a kernel. This is going to be the function that's called from inside int main or another function on a CPU, and it's going to actually be executed on the GPU in multiple instances. All these kernels have to be void. You don't get return values out of kernels. So anything that you want back from a kernel has got to be in the form of, you know, a pointer argument, and then you dereference them inside the function. If I say int BID, I get this variable block idx.x. That's the number, that's the index of the current block in the x direction. Keep in mind that this function is going to be executed over multiple instances, right? And for each instance, you get some block ID and thread ID for free. You don't need to set these things, block idx.x and thread idx.x. Those are given to you. I'm saying for each block, I want BID to be the current block ID. And if BID is less than n, I add the BID elements of A and B to get C. Does that make sense? Does this not make sense to anyone?
So here are you assuming that each block has only one thread?
Yes. That's what I'm assuming, actually. So thank you for telling me that. So I haven't specified the number of blocks and the number of threads here. That comes when I'm actually calling this function. When I'm actually calling, I specify the number of blocks and number of threads, and then I can say inside this function, block idx.x, do this. Any more questions? All right, let's go to int main. So I have vectors A, B, and C on the host side. Host stands for CPU, device stands for GPU. That's the lingo. And then I have pointers, dev A, dev B, and dev C. And those are going to be pointers with pointing to memory on the GPU. And these will be dynamically allocated, which is what I do here. There's this function. How many of you have not heard of malloc? So I think you're going to need to go, to really understand this, I think you're going to need to go over dynamic memory and pointers in C. On my website, I have some slides for that. You'll also want to look at a good book like Kernighan and Ritchie's C book or something. Or what? C prime? C prime. I haven't heard of it, but I'm sure. Yeah. Okay. Something like that. Well, as long as you know a reference that you like. I would read up on pointers, use of malloc, and other such things. The equivalent of malloc in CUDA is CUDA malloc. And you just say, I have to actually pass in a pointer to the pointer that I want to allocate memory for on the GPU. And I have to specify, as usual, its size. So I want to allocate, so dev A, dev B, and dev C are going to be vectors of n ints. And that's what I'm saying here. I'm allocating memory in the GPU to each of these. And on the CPU side, I initialize these CPU vectors right here. And then what I'm going to do is I'm going to copy them to the device. So CUDA memcopy is the function that copies the thing in the memory pointed to by the second argument to the memory pointed to by the first argument. This is stored in the CPU. This is stored in the GPU. I'm going to take n ints, that chunk of memory, out of A, copy to dev A. And there's this argument CUDA memcopy host to device. That's just a macro for some indicator that says, you know, I'm copying memory from the host to the device, from the CPU to the GPU. Is that clear? So typically I write my data on the CPU, then I use and I allocate memory on the GPU, and then copy things from the CPU into that GPU memory.
So that 1, 2, 3, the fourth is argument, right? Fourth one
Yes.
Argument, and that is an argument to a function name.
I'm not sure if it's a function name. I'm not actually sure. I haven't actually played around with it. I just know that that's how the syntax goes. It might just be a macro for, say, 0 or 1 or something that's predefined in some header. Now, I did a lot of work beforehand. This is when I execute my actual kernel. Remember? Add was up here. Took 3 arguments, A, B, and C. Here, I'm saying I'm calling add, but since this is a kernel, I have this thing between the function name and the parameters. Now what this is saying, these ugly triple angle brackets are saying, as I'm calling this thing with n blocks and 1 thread per block. So if you're just using 1 dimension of blocks and 1 dimension of threads, it's always going to be number of blocks, number of threads per block. And that does the addition. You have vector C on the GPU side. And what I'm going to do is I'm going to copy all of that which is in dev C back to C. Now I have CUDA memcopy, except now I have CUDA memcopy device to host. I had from host to device before. And then I print everything out. And then, as always, if you allocate something dynamically, you have to free it. And use this function CUDA free. Whereas free is for a CPU, CUDA free is for the GPU stuff. And you do that to every pointer. And if you don't, then you might have a memory leak. And if you run, that's the end of int main. Yep. You don't have to return 0 or anything.
I was just thinking at the end of execution when it cleared the memory for you.
I guess on good machines it might free the memory for you. I wouldn't count on it though. And see, people with state-of-the-art still have memory leak issues. I wouldn't count on memory being freed. So I run this. First I compile it. So NVCC stands for NVIDIA CUDA compiler or NVIDIA compiler collection. It can stand for both. Point is, this is what you use in place of GCC to compile things in CUDA C. You just say NVCC, your program name, -O for out, and whatever you want the binary to be. Execute the binary. This is the printout, and it gives me the right answers. Questions? All right, moving on. So vector addition is great and all. My next simple example is going to be the pairwise sum, or the cascading sum. This is the sort of algorithm that might be it's a low-level algorithm, very simple, but very, very useful. So I'll show you what pairwise sum is by example. So I'm going to use one block of 4 threads. So we're going to have 4 instances of this program executing simultaneously. And this vector has 8 members. And each thread is going to take a pair of numbers, this index and 4 places down, and it's going to sum those two. The second thread at the same time is going to take the next pair of numbers, the second one, and remember, index 1 plus 5, which is over here. Same thing with the next thread. It's going to sum the next pair at the same time, and the next thread. Now, once those threads are all going to sum those numbers simultaneously. And you can imagine the next steps are going to be sum this pair and sum this pair, right? That would make sense, right? Before we move on, though, we need to make sure all of these sums actually completed. We have to have these numbers to begin with to continue summing things, right? And so we want to synchronize our threads. We want to stop here, synchronize all threads. Now, one reason for having blocks is because I can synchronize threads within blocks very easily. It's very hard to synchronize blocks. But since I have one block, I can do this. I can synchronize all my threads to make sure all these numbers have been calculated before I move on. And then I move on. Take this pair, sum it up. Take this pair, sum it up. Before I sum these two again, I synchronize threads again. And then I sum this last one, these last two. And that's the pairwise sum. And so synchronization is waiting for all parallel tasks to reach some checkpoint before I continue. That's just for reference. As I said, threads within the same block can be synchronized easily, but in general, don't try to synchronize threads from different blocks. It's very inefficient. Now, if we compare this to the sequential sum, I have to take n-1 pairs sequentially and sum those up. And this requires log base 2 of n sequential stages. No. This requires n-1 sequential stages. The sequential sum does. The pairwise sum only took log base 2 of n sequential stages, where n was the length of the vector. So this becomes much more efficient if you can do this in parallel, which you can. So here's the pairwise sum. I have all the same libraries except I include the math library. So for this particular implementation, I'm assuming all of my vectors have a length of a power of 2 for things to be convenient. This is just a function to fill the vectors with some random number, each element with some random number. Here's just a function of print. You can do those in regular C. I'm not going to go over those. Now here's our kernel that does the pairwise sum, that's psum, of some vector of floats. Now I use float instead of double because some earlier GPUs didn't have doubles. They couldn't support doubles. So the most recent ones do support doubles, but I use floats anyway just to be safe. Now, going into this code, so I quickly simplify things. Thread idx.x is the index of the thread within your block, within the current block. And then you get block idx.x. You don't need to define these again. These are given to you for free. And they're going to be different for each instance, for each parallel instance of this kernel. But for each thread in each block, I do this. So you can imagine that if this were to be done on the CPU side, this would probably be written as a for loop over t and over n. This is one particular instance of what's going on. And this while loop is exactly what I showed you in the picture. You kind of have to stare at the pictures and stare at this to kind of understand what's going on. But while what I do here is while n does not equal 0, so n is the length of the current vector that I have to sum. So the vector collapses in half at each iteration. N is the length of the current vector that I use. I say, if t is less than n, so if our number of threads is less than n, actually, no. I'm sorry, n is not the length of the vector. N is half the length, actually. Half the length of a vector, because we have I said a couple of things wrong here. So this is not block idx.x. This is block dim.x. This is the number of threads in the x direction. So this is an upper bound on t here. And since there are half the number of threads I showed you as there are, so before I had a vector of 8 things and 4 threads, similarly, you want half the number of threads as there are elements in your vector. So, and what I do here, so n is half the length. And if t is less than n, that means that's just safeguarding against too many threads. I take element t and element t plus n. So you take this element plus the element halfway down and sum it up. And each t gets a different pair along that vector, right? This is all going to be, and for all t, this is going to happen simultaneously. After you do these summations, you want to synchronize your threads again. And for the next stage, I only need half the number of threads as I did for that previous step. So I divide n by 2.
So physically, what does sync threads do?
Sync.
It just reduces the number of threads? Or
Nope. Sync threads stops all the threads until all the threads have completed this sum. So sync threads says, thread number 1, you need to wait until thread number 2 is done and has reached the same point as you. That's what it does. So before it goes on to do some more summations, all the threads stop here, and I can assume that n is only divided by 2 after all these summations have been completed. Otherwise, you might run into trouble. And you just keep doing this for smaller and smaller n, and once n is 0, you're done. And the rest of the code here is just allocating memory and calling psum with the appropriate number of threads. So I'm going to use one block, and capital N over 2 threads, where capital N is the number of elements in the vector. So if I go to my main function, v sub h and v sub d are the host vector, the copy of the vector on the host and the copy on the device, respectively. I allocate CPU memory. I do CUDA malloc to allocate memory in the GPU. I fill the host vector. I print it out just to see what's going on. I copy the host vector to the device vector, as I explained before, CUDA memcopy. I call this psum. I use one block and capital N over 2 threads per block. So I need half the threads as there are half the number of threads as there are elements in the vector. Once I'm done, I copy it back. I print it out. I free my vector on the host, and I call CUDA free to free it on the device. And that's my program. Make sense? Yeah? And I run it by compiling it and running it in the usual way, and it works. This is part of the example code that's online. On my web page for this talk and all talks, you'll have example code. You can go to the course web page for this, and you will have this example code, and you can run it yourself. This pairwise sum is part of a whole class of calculations called reductions. So pairwise sum is and pairwise multiplication are reductions. Pairwise multiplication is exactly what it sounds like. Instead of summing things, you multiply pairs of things. And reduction is just an algorithm that applies a binary operator on a vector to produce the scalar. You just replace summation by whatever that binary operator is. Scans are sort of in the same family as reductions. They're similar kinds of algorithms, but a distinct class from reductions. They're also called prefix sums. It's an operation that applies. It's a algorithm that applies an operation on a vector that produces a sequence of partial reductions. So a sum scan would produce a sequence of partial sums of a vector instead of just the pairwise sum of everything. The last element would be a pairwise sum. So you can compute the sequence of partial sums. And that's it for the pairwise sum. Moving on to my next program, k-means. This is a little two-dimensional k-means program I wrote in the spring that I'm going to show. This is not my plot. This is Dr. Moitro's plot from when he taught k-means in Stat 580 in the spring. But the idea is I have capital N vectors in Euclidean space, and I want to partition them into k groups. Now, most of you know k-means, but I'm going to go over it anyway, just so I can refer back to my notes when I'm explaining this. So, say you have a bunch of points and a bunch of cluster centers. Here we have each circle as a cluster center. So there's a red cluster center, green, and a blue. And each of these gray squares is one of my points. And I want to cluster. I'm going to cluster these points into 3 groups. And I'm going to do this in 3 steps, where step 2 and step 3 get repeated over and over again. Oops. This is step 1, where I actually pick the cluster centers. This is usually non-trivial. You have to do a good job of picking the cluster centers, but here they are. I've picked them somehow. Step 2 is I assign each data point to its closest center. So I observed in the previous step that this box is closer to red than to green. So I assign it to this cluster center. This box is closer to green than to red. So, and this box is closer to green than anything else. So I assign these to green. Everything over here to blue. And I get this partition. That's my first clustering, and that's what it should look like at the end of step 2. Now, I want these cluster centers. These cluster centers are also points. And at the end of my algorithm, I want these to be the means, each cluster center to be the mean of the points within that cluster. But right now, since I've just assigned the points, I've just repartitioned the points, these cluster centers are not actually cluster means. So I'm going to take the mean inside here, the mean inside here, mean inside here, and reassign in step 3 those cluster centers to be those cluster means, which means the cluster centers are going to move. And since those cluster centers are going to move, I have a different partition of points now that I need to make. And so I recluster. I go back to step 2 and assign things to clusters. And since I reclustered, I need to recompute the means again. And so I go back in from step 2 to step 3 until convergence. That's classic k-means. Now there's a lot of opportunities for parallelism here. Whoops, I forgot that I had a slide for repeating step 2. Here's reclustering. So step 2, here's one way to parallelize k-means. Very simple, hopefully pedagogically friendly one. Step 2, you assign points to closest cluster centers. There's a lot of independent calculations going on that can be run simultaneously. So what you can do is you can spawn n blocks. So n is the number of points with k threads each. K is the number of clusters that I want. So we have n times k threads. And we let thread nk, the k thread within the nth block, compute the distance between data point n and cluster k. And what that does is it computes all of these distances at the same time. No for loops that depend highly on the number of data points. You can do this all at the same time. So you have all these distances now. And after you compute the distances and you want to use those distances, you've got to either synchronize the threads within each block or go to another kernel. In my example, I don't actually synchronize. I go to the next kernel. Kernels happen sequentially. And using these distances after you've synchronized somehow, you can take n blocks with one thread each, or one thread within each block. You can compute the minimum distance for point number n, and assign that point to the corresponding cluster of minimum distance. And for each point gets reassigned independently of each other point once you have those distances computed. So you can work with all the points in parallel. That's another opportunity. Step 3, it means computing cluster centers, which you can do by spawning one block for each cluster. And within each block, particular to each cluster, you compute the mean of the data within the corresponding cluster. And that you do with multiple threads in that block, ideally. And here's how I do it. So first of all, I have a two-dimensional matrix with distances. A key thing to keep in mind for CUDA, it's very hard in CUDA C to work with two-dimensional, three-dimensional arrays. You're going to want to work with one-dimensional arrays as much as you can, just because it makes things a lot easier. CUDA still hasn't gotten out of this sort of graphics mentality when it comes to two- and three-dimensional arrays. You'll either have, if you really want to do two- and three-dimensional arrays, you'll have to sort of think about it like a graphics problem, and you'll have to do some really confusing syntax to actually get this to work. It's not nearly as natural as arrays in C yet. They're working on it. So I have this indexing function. It's a macro. Usually use a macro, and it just what it does is you put in the row in your current column, number of columns, and it computes that corresponding element of that 2D matrix. But really what this is what you're really working with is a one-dimensional array, but you can just plug in this where the index goes and work with it as if it were a 2D array. And that's what this does. I use that a lot, and it's very nifty. You also want to have a macro for error checking. I've discovered errors in CUDA code that I would never have been able to diagnose had I not done error checking for allocating memory and writing memory back and forth. For CUDA memcopy and CUDA malloc, you need error checking always. And here's a little macro to do it. I call it CUDA call. So you'll basically, X is going to be your code to do something like CUDA memcopy or something. CUDA success and CUDA failure are things that a CUDA malloc or CUDA memcopy might return to you. You'll want to check that. CUDA success is defined in some header, and if you're not successful, then you can print out what's going on. So you can print out where your error is. The file, _file is just your file. You can print out your line number, _line, _. And there's this nifty function called CUDA get error string, which turns some numerical error code into a description, a string of what's actually going on. And you can print that out of CUDA get last error, and this returns some numerical code. This function turns it into something you can actually read, which is very nice. And then you exit failure. You don't want to say return failure because you could be inside of another function, and your program could continue and crash. You want to make sure to stop your program right there. So here's my a couple of kernels for step 2. That's computing the distances, computing the nearest cluster center. To compute the nearest cluster center, I need to compute these cluster distances. I call my function getDist. Here's a one-dimensional array of distances, which I use as if it were a 2D array. X and Y are vectors of floats, and X has the vector of X coordinates, Y is the vector of Y coordinates. This is a simple 2D k-means. I didn't go more than 2 dimensions here. Yeah. And mu x and mu y are the vectors of x and y coordinates of the cluster centers. So you've got points and you've got cluster centers over here. Now, so I call this kernel, and I get a block, and for every instance, I get a block index and a thread index. Those are I and j. So j is the index that I'm going to use for the cluster center. I is the index that I'm going to use for the point. And you can imagine after this point, you can imagine you're inside a for loop and do everything you would otherwise do with I and j. And I'm going to say that distance ij, here's my indexing macro here. So I'm using distance like it's a 2D array. So element ij, the ith point in the jth cluster, is just going to be the Euclidean distance. So that's what I'm doing here. I'm going to take the squared distance in the x direction from its mean, add on the squared distance in the y direction from its mean. And that's all I'm doing here. So this kernel computes all the distances. Now what I could have done is sync threads, call that function sync threads right here, and then move on to compute the nearest cluster center once I had those distances. I decided to separate this step 2 into kernels. Compute the distances, get dist, and a function that I call regroup, which just takes those distances and reassigns cluster centers. So I call this with let's see, multiple blocks, but only one thread. And I'm calling, so I is the index for your point. And this code just calculates, it's sequential in across clusters. What I do is just calculate the minimum distance between point I and all the clusters. And the cluster with the minimum such distance is the one that point I gets assigned to. That's all this is doing. And I should say this vector group that I passed in is just the index of the cluster for each of the current cluster for each point. So group is a vector of length capital N, and it just says, what cluster does point I belong to. So I have a kernel to get the distances. I get a kernel to assign the points to the nearest cluster. Step 3, I parallelize 2. Step 3 is recomputing the cluster means once I've recomputed the clusters themselves. So I use the function clear for that purpose. So I have these vectors, some x and some y. That's the sum of the x components and the y components in within each cluster. So these are of length capital K or lowercase k in the code sense. Nx and ny keep track of the number of points that I have in a particular cluster. I don't know why I chose, one for the x direction, one for the y direction. I didn't really need to. But the point is, I have to have them all start at 0, and I have a kernel. I have an entire kernel just to do that. Now I have this function recenter step 1, and that's just computing in parallel. I'm not going to go over this in too much detail, but in parallel, I'm computing the sums in the x direction and y direction of all of the of all the points within each cluster. I'm doing that all in parallel, and I'm counting the number of points in each cluster. I really only needed nx. I didn't really need ny. And then I take the sums, divide them by the number of points in each cluster, and I get the cluster means in the x and y directions in recenter step 2. I'm going kind of fast, but I'll go over this in more detail 4 weeks from now. And then I put all the kernels together in this function k-means. Now k-means, notice there's no global in front of this. There's no global prefix. So this happens on the CPU side. And sure enough, I loop over the number of iterations that I want, n reps, and I execute these kernels sequentially. First I get the once I have the initial values, I assume that I have initial values for the cluster means. First I get the distances between each point in their clusters, n blocks, k threads per block. I regroup them. I regroup the points into their clusters based on the distances that I calculated. I clear the information that I'm going to use to compute the cluster means. And then I call recenter step 1 and recenter step 2. They're both kernels with k threads and 1 block. I compute this to recompute the cluster centers. And so that's my main k-means function. I also have functions to read the data and print the results. I'm assuming the data include mu x and mu y, which are initially they are initial values for the cluster centers. And that's the code that I'm going to go over here. Int main just defines everything, n, k, group, x, y, mu x, and mu y. And I have copies of all these variables on the device because I'm going to copy my data to the device and then read everything back. And I call CUDA malloc a bunch of times to create memory for these things on the device. And notice I have CUDA call wrapped around every single one of those because there may be a problem where you can't allocate memory anymore. This summer I had a problem when I was writing an MCMC and I was trying to store all the iterations of my MCMC on the device, and there just wasn't enough memory for it. But fortunately, I was using error checking. I was using CUDA call, which told me you don't have enough memory anymore. And so I had to restructure my program because I was using up all the GPU's memory with my MCMC that I wanted to run for 1,000 iterations on 50,000 parameters, which is, of course, going to take a lot of memory. But I didn't think of that before. And this is very useful information that I got from just writing an error checking macro. It's not only good practice, it's essential. All right, moving on. I do that for CUDA mallocs, and I do that for CUDA memcopy. And I do that for CUDA free later. So I do the error checking here. This is where I copy everything. Once I've initialized things, I've assumed that I've read the data here and copied and allocated memory in the GPU. I copy things on the host to the device. That's CUDA memcopy. I actually run my k-means here. Notice this is not a kernel, but it's a function on the host that has a bunch of kernels in it. Then I copy the results back to the host. I print everything out. And then I clean up. I call free, and I call CUDA free. When I call CUDA free, I need to do my error checking here. Now, I'm not quite done yet with things to show you. First of all, you can download this from the website. It has a zip file, and in the zip file is a make file. So you can just hit make to compile everything. So the CPU version is just compiled with GCC. It's a .c file. I use the flags wall, ANSI, and pedantic just for debugging purposes, and ANSI actually just because I like the ANSI standard. Now, the compiler options for NVCC are a bit different. In general, they're different because you'll have to link some CUDA libraries usually. In this one, I didn't need CUDA libraries, but I needed to prefix my flags ANSI and wall with this flag called compiler options. That took a little bit of digging to find on the internet. Unfortunately, a lot of this documentation for CUDA C stuff is missing. Next, I run my program with this dot slash GPU k-means, but I run it through a program called CUDA memcheck. How many have you heard of Valgrind? Heard of Valgrind? So Valgrind is an amazing tool for pure C code. It's used to diagnose memory leaks, and it's used to diagnose things that you've uninitialized use of uninitialized variables. Maybe you've declared a variable, haven't initialized it, but used it anyway, even though there was garbage in that point in memory. And you don't want to base your calculations on some garbage value, so you run Valgrind to make sure you've defined all your terms before you actually use them in code. And Valgrind does a whole bunch of other things too. And it's a bit hard to use if you don't call it early and often, but it's great. Unfortunately, Valgrind doesn't really do the job on the GPU. It'll think that you call, it really can't see what's going on in the GPU, so it'll assume that there are memory leaks on the GPU when there actually aren't memory leaks. Valgrind will tell you, it doesn't let any errors pass by undetected, but it also falsely detects things that are actually correct.
What do you mean by memory leaks is overflow? Overflow arrays and stuff?
What I mean by memory leak is when you dynamically allocate something but don't free it. If you don't free it, that's a memory leak. So for detecting memory leaks on the GPU and other GPU style, uninitialized value errors and things like that, for everything on the GPU side, you want to run through CUDA memcheck. And all you do is you say CUDA memcheck, whatever your program is, and it tells you a bunch of things. And you'll see what you want is error summary 0 errors. That is what you want. If you run CUDA memcheck and you get errors, you will want to diagnose them. The other thing it might tell you is, no results file found. And that may be because if it can't find a results file, that may be because within your program you changed directories, and when you changed back, it wrote a file somewhere else. And so you want to search around for a results file. And if that results file is blank, then you're good. I also want to, but not only did I do things on the GPU, I did things on the CPU as well. Usually you'll have calculations going on both areas. So I want to run it through Valgrind as well, but just take the results with a grain of salt. I run Valgrind, GPU k-means, and it'll give you your, the information on, what Valgrind is and what the command was. And any flags that you have, by the way, you can just put after. Valgrind won't care. CUDA memcheck, you can put any flags, runtime flags here, and you'll be good. And it'll give you a bunch of warnings that you don't need to know about. It'll say, warning, set address range perms, large range. That's because you're allocating memory on the GPU, and that's why there's no access here. So that you can ignore usually. It's also more verbose than CUDA memcheck. It'll give you, a summary of what was dynamically allocated. That's the heap summary. When you're programming, there's an area of memory called the stack, and a memory location called the heap. The stack is what you allocate statically. The heap is what you allocate dynamically, and it'll tell you what's going on at the heap. What you usually want to look for with Valgrind is the leak summary, and for me, it usually tells me that there are 16 bytes lost in one block. Block not in the sense of GPU parallelism. Block is in the sense of block of memory. You can in general ignore that unless you just have a ton of memory leaks reported, in which case you'll get individual errors. you'll want to do, so inevitably you're going to have, it's going to show you some memory leaks if you do stuff on the GPU, but you don't want to take it too seriously. And as always, you want error summary, 0 errors from 0 context. So you don't really need to worry about the suppressed errors. That's sort of, beyond your control. That's sort of the behind the operating system doing something that Valgrind doesn't expect. And the great thing about Valgrind is it'll tell you what to do. If you encounter errors, it'll say, run leak check equals full if you have memory leaks and it reported where the memory leaks are and you want to see where those actually are. It'll sort of walk you through that. Bottom line is, you always want to use CUDA memcheck and Valgrind. And then you can run your program for real. GPU k-means computes, outputs a couple of files that tell you what the clustering is and what the group means are. Here's where I started, my initial values. Here's the clustering when I finished. I don't know if this is correct. The correct number of clusters in this problem should, just by looking at it, I think all the points should be in the same cluster because they're a lot closer together. But I just wanted to give the program sort of a challenge. If I separated them into clusters visually to begin with, this algorithm would converge really fast, and I wanted it to have some sort of challenge. And that's k-means. Any questions?
I know how to post. I don't know enough terminology yet. But you have blocks and threads. But this is the first time you're seeing that you have threads that are different numbers of threads in each block.
Yes.
And it's dynamic also. It keeps changing from iteration to iteration. From each of these times that you go through the steps.
Well, actually, the number of
Well,
the number of threads and the number of blocks doesn't change from iteration to iteration because they're always endpoints in k clusters, and they're going to be let's go back to the k-means function. So here where I call my kernels, so n is the number of points and k is the number of clusters. I'm calling this kernel with n threads and n blocks and k threads per block. I'm calling this with n blocks and 1 thread per block, 1 in k, 1 in k, 1 in k. Again, that actually doesn't change from iteration to iteration.
So that means when you are you're computing distances, right?
Right.
So the distances change.
They do. The distances change.
That means we are computing these distances in different blocks.
Oh, that's all right. I'm computing all the distances within the same point in the same block. So I'm computing the distances. Each point gets a block. And within that block, I'm computing all the distances.
So this is nothing to do with the actual the k-means thing, how we are doing computing.
So this is actually the most basic form of k-means. This is not sort of the state of the art as far as algorithms are concerned.
I think about it. So I know I got confused. I was confused thinking that when you do that syncing thing,
Yeah.
you're losing something because you have to wait until some computations are done.
Yeah. You don't actually lose that much. It turns out a lot of threads are actually grouped into groups called warps, and they execute in lockstep, which means groups of threads execute at the same time. So synchronizing threads in that case, at least within warps, doesn't actually slow anything down. You do lose a little bit of time when you have a bunch of threads, but for really large problems, the payoff is so great that the synchronization step doesn't actually cost as much, relatively speaking. But you're right. You do lose some time synchronizing threads because you have to wait.
If there's a big difference between the number of threads
Yeah.
Right?
Yeah. Yeah, if there are a lot of clusters, you'll have a lot of threads in each block that you need to synchronize. And that increases with the number of clusters. So if you have hundreds of clusters, or maybe even thousands of clusters, then maybe that'll be a problem. But if you have only, in this case, you have 3 clusters, maybe you'll have 10 clusters in regular problems, so you only have to sync 10 threads. That's part of the reason why I chose to have each point get its own block.
Thank you.
You're welcome. So that's at least my little 2D implementation of k-means. It was just for pedagogical reasons. But for k-means in higher dimensions and better algorithms of k-means, you'll want to look to people who have implemented Hartigan and Wong's k-means, which is a much better algorithm than this classic Lloyd's k-means, which I implemented here. I only have 5 minutes, but I'm just going to touch on an example of an MCMC. I'm going to do this in a slide set where I don't step through the lines, just so I can get through this in 5 minutes. But this is an example from Stat 544 with Dr. Jared Nemi, who's obviously you guys, most of you know him. We worked with the bladder cancer data set, and in this data set, we have data for each county in a collection of counties in Iowa, and we have what some people recorded were rates of death from bladder cancer of white men from 2000 to 2004, actually in each county in the USA, not just in Iowa. So if we let k be the index of the county, we have y sub k as the number of deaths in county k. If n sub k is the number of person years divided by 100,000. That's a function of how long we observed these people. And so these are data. Now we let theta k represent the number of expected deaths in 1,000 person years. And we have this hierarchical model here. So at the top level, we have the data are Poisson counts, we assume. And we parameterize, we put a prior on theta k. So for each county k, theta gets the same prior. So this gamma, alpha, beta. And we give uniform priors, hyperpriors to alpha and beta. And now you notice is we have a lot of counties. We have thousands of counties, about 3,000 counties. And what we can do, we do in a Gibbs sampler is we sample iteratively from the full conditionals of all the theta k's and alpha and beta, right? Standard MCMC. Sound familiar? Hopefully. We have a lot of counties. So what we can do is we can parallelize the sampling theta from its full conditional. So we sample, since all the thetas are IID, when we go to sample the thetas, we can parallelize the sampling of thetas. We can spawn, a total number of threads equal to the total number of counties, and sample these thetas independently. And we can achieve a speed up that way. So this is just one example where you can parallelize an MCMC. Very simple, embarrassingly parallel here. I don't have time to go through, I have only a couple minutes. I don't have time to go through the full detail, but so if I were to actually do this, I first write out the joint distribution of the thetas, alpha and beta. From each of these, I write out the full conditional of theta, which is actually just a gamma distribution. So I can simply draw from these gamma distributions in parallel. This implementation has, has a metropolis step for sampling the distribution of alpha, because this is not in a convenient form that I like. I use a metropolis step for this step, and I sample from a truncated gamma as it's when I get to the full conditional of beta. And I go through in detail how this is done in the code, how this random walk metropolis for alpha happens. And the gamma sampler, there is no good gamma sampler in NVIDIA's libraries. You have to implement a gamma sampler yourself. But this one has a really high acceptance rate for your shape. If your shape parameter alpha is greater than or equal to 1, this algorithm performs very well for the gamma sampler, and it's in the slides. And it has an acceptance rate greater than 95%, a lot greater than 95% when your shape parameter is higher. And here's the metropolis step. And the code was not created by me. I only modified it, but this one of my peers, Zeb, created this code, and his email isn't in here, but I can get you in contact with him if you're interested in this code. I can also answer questions about this code too, since I modify it, I look through it, I understand it. So this is the code for that MCMC. The code is online, and you can take a look at it. And that's all I have time for. I was planning to do an OLS sampler, ordinary least squares, and illustrate how the linear algebra libraries, but I don't have time for it. I will devote an entire lecture to that, though, later. So feel free to come back. I'll make an announcement. Any questions?
So with, in that, say, MCMC example, or like a simple for loop, if I'm writing a code in R, can I use GPU tools? So for example, that MCMC code that the GIF sample that you just showed, I want to do since theta's are conditionally independent, I want to do that in GPU.
So
GPU tools for doing that?
Unfortunately, no. GPU tools, you can't parallelize for loops in GPU tools. Yeah, GPU tools, I mean, it's not built like that. I think somebody should write a package in R that will take for loops and write them as kernels, as GPU kernels, but it doesn't exist yet. I mean, there's no equivalent of the for each or multi-core packages for the GPU in R. There should be, though. Thanks for the idea. Anything else? Well, great. Thank you for coming. And if you didn't understand everything or something, then please come to my later talks. I said everything that I will want to say in the introduction, so you need not come to the introduction unless you want to hear the introductory spiel all over again. But the first new talk for you guys will be 2 weeks from now.